Okay, welcome. What we're going to talk about now is, and we're going to change subjects quite a bit from the ADS that Jack did a good job on. You might notice up there it says Rick Overdorf. He's not here. My name's John Hansen. I work in Santa Rosa for Agilent. Worked for years on signal sources and also signal analyzers. But you can see the topic here is about signal sources of pulsed waveforms. And specifically RF pulsed waveforms. So it's not a simple on-off anymore. CW pulses are actually relatively simple to generate with any of today's signal generators. But that's not what's used primarily anymore. Pulses, particularly for radar or testing electronic warfare systems, have considerable amounts of modulation, distortions, different things that need to be embedded on the pulse, modulation on pulse, in order to realistically create an environment that's needed for today's systems. Specifically, radar was the example here, but of course these issues apply to any pulsed waveform, but of course radar is probably the paramount use case here. So what are people looking for designing these systems? Well, you're the ones that do that. You probably know, but better than anybody, we need a deep on-off ratio in order to realistically recreate something that comes from a radar exciter. Of course, we want a big dynamic range because that pulse has to go out, reflect off some small target, come back, and of course it's being attenuated by the fourth order as it comes back to the receiver. So a lot of on-off ratio and dynamic range are going to be critical. The pulse needs to have high fidelity. Today's radar systems, of course, we're starting to track targets that are moving very slowly. In other words, what are the military terms as dismounts. So these are people who are walking along a trail or even in a busy urban environment. So high fidelity means very low phase noise, being able to see Doppler shifts very close to the carrier. Long playback, of course, that's required for a lot of different waveforms, but in radar it's specifically needed because the signals aren't necessarily repeating. You know, a lot of times we work with pulse waveforms that are just repeating same thing over and over again, but that's rarely the use case. The use case is going to be a flight of a missile, radar-guided missile, where the return signal and the transmitted signal are getting closer together. The distortions that are seen are going to be varying with time in a very slow rate. So a long playback is critical, and you might say, well, I just need a deep memory source. I'm just gonna stuff bits over a bus to my signal generator, and I can have hours of data because I can have terabytes of RAID array or some other huge solid-state memory resource. The key there, though, is getting that data across that bus. You know, and PCI Express, you know, is slowly addressing that issue, but in the current time, the bandwidths that are required for modern radar are wide, so it takes a lot of bandwidth across a bus to shove data from a large memory into your arbitrary waveform generator or signal generator. So what are the alternatives here? And that's what I'm going to talk about. So sources or vector signal generators, we all like to have them. They're not the sexiest instrument in the world, but everybody's got to have a signal generator to stimulate their system. Output power, critical. Automatic level control, part of any vector signal generator, allows you to maintain a specific power level. So what are the issues when you start talking about pulse waveforms? Well, they can be kind of unique in that the power is going on and off. So what do you do about the off time? Well, you need to be able to gate that off time using markers from the arbitrary waveform generator to your pulse modulator, and I'll talk a little bit more about that. In fact, right now, the IQ and pulse modulation is something that we need to combine. So there's basically two types of modulation, and we're going to overlay one on the other. And you might say, well, I can make a pulse with an IQ signal. Well, you won't get the on-off ratio or dynamic range that you really need, so you really need to overlay an analog pulse modulator onto that signal. Now, some of the issues there are how do we align those, and I'll talk about that, I think, on the next slide or two. RF flatness, phase flatness, modulation bandwidth, all issues. The bandwidth required for simulating signals or simulating multiple signals, for that matter, is getting much wider. Of course, Agilent has arbitrary waveform generators that are very high performance, high dynamic range, wide bandwidth. You can't hardly see this, so I'll try to trace that. You can see that if I'm using just an IQ only signal, I get about 60 to 70 dB of dynamic range. If I overlay the pulse modulator, I get about 80, 85, even 90 dB of dynamic range. So that's why we have to do that. We need to use both modulators in tandem in order to generate a realistic signal. Now, how about pulse width? How narrow can we make this? One rule of thumb that we have, and that is incorporated into the tools that Agilent has, is that you really need about 3 sample points or about 3 nanoseconds of rise and fall time in order to accurately recreate a pulse, whether it's a trapezoidal pulse or if you want to create different types of shaped pulses, sinusoidal, rise and fall. These are different things that require at least 3 sample points or 3 nanoseconds. Kind of a rule of thumb there in terms of pulse shaping. Now, you could actually use a single data point in your arbitrary waveform generator to generate a pulse. Not sure how that would make it through the RF chain, though. So you really need to figure that a minimum pulse width may be at least 3 nanoseconds rise, 3 nanoseconds fall, a few nanoseconds of on time. And so you're really going to get, with an arbitrary waveform generator, or today's arbitrary waveform generators, you know, minimum pulse widths of maybe 10, 15, 20 nanoseconds. The key there is as they get narrow, they get harder to level. We can't really use the automatic level control anymore because it doesn't work fast enough. It doesn't operate fast enough on the pulse, and it adds more distortions than it helps. So some of the minimum pulses you can kind of see here, 20 nanoseconds, 5 nanoseconds. So minimum pulse width, you can get some pretty good shaping just using what we call power search, which is kind of a sample and hold function within your vector signal generator to grab the level and keep it. If you have short bursts of pulse, you'll also notice one of the problems with an automatic level control is it takes time to find its level. So you might, the first 4 or 5 pulses in your pulse train might be amplitude errors there. So in the case of turning the ALC off and using a power search, you don't have that issue either. Any questions so far? We're doing out of time. Okay. Now, also on this slide, and it's kind of hard to see over on the side, it's kind of an exaggerated view of how the timing between the pulse modulator and the IQ signal coming from your arbitrary waveform generator, the alignment issues that you might have. Of course, you know that you're trying to send a marker signal from the ARB to the signal generator, to the pulse modulator to tell it when to come on and off. But it doesn't really account for delays. So we need to be able to account for delays and shift that window of the pulse modulator right over that IQ pulse that you've created in your ARB. And here's some of the issues. Here's one where we've exaggerated what we call the porch, where the dynamic range of the IQ signal kind of meets the dynamic range of the higher dynamic range of the pulse modulator. And we've aligned it pretty well here, but if you misalign by just a few, couple of dozen nanoseconds, you can have corrupted pulses. And your pulse modulator is actually distorting your pulses rather than helping the dynamic range. So this is something that has to be taken into account. Now the bottom line here is, and I'll just briefly say this, is that Agilent has software tools that make all of this transparent to the user. Aligning the pulse, the pulse modulator along with the IQ signal coming from the ARB, we can align that. We also automatically do the leveling for you. So enough of the commercial meshes there. But these are some of the issues that we have to contend with when creating pulse waveforms, particularly those that are modulated. Now, we may want to do some amplitude and phase corrections on our waveforms. And one way, the classic way that we do that with signal generators, is to take the waveform, play it, measure it with a signal analyzer of some sort, could even be an oscilloscope, perhaps put a bank of or a number of tones for a multi-tone signal, measure the flatness, and then distort or pre-distort that waveform file, download it again into the arbitrary waveform generator and play it back. So that's the classic way. Well, okay, here comes another commercial message. The key thing is that's kind of done offline. It's not real time, right? Well, Agilent has a signal generator, the MXG signal generator, and all this is in our booth, so you can come and see what we can actually do in our booth. It does it all in real time. And it does not only baseband corrections, aligning the offset, the INQ offset, and the INQ skew going into the IQ modulator of the signal generator, it also corrects the RF path as well. And it does it all with a very fast DSP and does it in real time. So you don't have to do this anymore. You can adjust and get very flat phase response, amplitude response across the 160 megahertz bandwidth with the MXG generator. Now you might say, well, 160, okay, I'm doing 2 gigahertz chirps. You know, for my situation, I have really high resolution synthetic aperture radar, and I need something wider. So here's the flatness that I just talked about with the MXG. We actually have a microwave signal generator with a very wide band IQ modulator, along with a very wide band arbitrary waveform generator, a 2-box solution that can give you up to 4 gigahertz of bandwidth. And you can see before distortions, and of course in this setup, it's not real time. It's the classic non-real time method of correction. But you can see we can get within a few tenths of amplitude flatness across the entire bandwidth. So 4 gigahertz. Now, we also have ability to do other kinds of flatness across wide bandwidths with power meters. We can just simply connect one of our USB power meters to the X-series signal generators and do a flatness calibration right at the output of whatever you're hanging on the output of your signal generator, which could be amplifiers, filters, switches. And you can do right to this reference plane here, you can flatten your signal. And this is a classic way of doing it. It's just that within the signal generator, it's all done in firmware. It's a one button cow. So the arbitrary waveform generator itself, let's just talk quick about that. There are a few issues there that we want to talk about, nuances, if you will. And let's get right into it. If we're sampling, and we, in this case, we've turned off our our anti-aliasing filter, and you can see if our sample rate is lower, in this case 1.25 gigasamples, you can see all of this aliasing distortion here in a sin X over X type of shape. If we oversample, if we just double our sample rate, we can push those with the purple traces here. We can push those out much easier to be able to filter away with an anti-aliasing filter. So the ability to do this, what does that require? It requires very high sample rate, and of course the bottom line that for me is that we have ARBs that of course can sample at very high rates, being able to push these out to areas that make them quite easy to filter away. So aliasing is another issue that you have to consider when using an arbitrary waveform generator to create a pulse signal. Memory management as well is very key, because if you need to align pulses, of course, if you're doing using segmented memory in order to conserve memory within your signal generator, you want to be able to align these different segments such that they match the blocks of memory for which your arbitrary waveform generator writes to its memory. Of course, I kind of butchered that, but suffice it to say, each sample is not accessible out of a deep, very fast ARB memory. It's written to the memory in blocks. And in case of our very wideband arbitrary waveform generator, you have to you write it within blocks of 48. So your waveform has to be multiples of 48 samples, or else you run into some issues at the end of the waveform. Our tools, our software tools, once again, account for that and do the alignment by segmenting the pulses in such a way that they always end up as multiples of 48. We basically, to conserve memory, we create pulses within the arbitrary waveform generator, and we create off time as a segment. To conserve memory, that off time segment is just played out of one little portion of memory over and over again. So that's how you can save and conserve memory using segmenting and sequencing of your waveforms. As you get down to more and more narrow pulses, perhaps you want to combine those such that they don't exceed the 48 points of the memory block that you have to write for your waveform. So there are methods to be able to account for specific memory blocks within your arbitrary waveform generator. And all of this is done automatically for you with Signal Studio for Pulse Building, which is one of our waveform creation software tools. This slide says kind of the same thing. It just kind of shows the user interface of our software tool. And I just had a couple more things about creating pulses with ALC on and off. So to summarize, of course, we need to be able to drive the IQ modulator or the pulse modulator with a marker signal from our ARB. Then we need to be able to know the platform that we're actually generating the signal on. Once we know that, we know how much shift, how much fixed offset in time that we need to put onto our pulse modulator in order for it to completely window our IQ signal. And that's what we need to do, and it's actually quite hard to do in practice. We have software that does that for you. Okay, and here's some examples that I won't dwell on. We can show you this in the Agilent booth just across and around the corner. So just to summarize, we have a tool that takes care of all these nuances, makes them transparent to you. If you want to build your waveforms in MATLAB, we can help you with that, but just keep in mind there's a whole lot of nuances in terms of timing, amplitude, and dynamic range that need to be considered when creating your own pulse waveforms from scratch using an arbitrary waveform generator. Any questions? I'll kind of leave it at that.